Welcome back, everybody. We're going to continue our discussion of surfaces and surface area, and now it's time to talk about parametric surfaces. So way back in chapter 13 we talked about parametric curves, and we were able to parameterize curves using a single parameter t because curves are one-dimensional, so we just need one parameter to map out that curve. Now we didn't deal too much with how to parameterize curves because the exercises in the book basically gave all the parameterizations to you except for those involving line segments. So we spent some time parameterizing line segments, but that's about it. Now we're going to learn how to parameterize surfaces, and we're actually going to spend some time talking about how to parameterize a surface, and there are exercises in the book that help you practice how to parameterize a surface. So you're going to need to learn how to do this, and it's not always intuitive. It can be a bit frustrating, but with enough practice, you'll start to get the hang of it. So if we want to parameterize a surface, we're going to use a vector equation just like we did for curves. We're still going to call it r, but now it's going to be a vector function of two variables. So we're going to have two parameters. We're going to call them u and v, and we need two parameters because now we're mapping out a surface. A surface is two-dimensional. Okay, these vector functions are still going to have three components because we're talking about surfaces in 3D. Well, we can't have surfaces in 2D, right? We only get curves. So we have an f component, a g component, an h component. Each of those component functions are functions of two variables. And we're going to have some bounds on our parameters. Now, the way I've written it, these bounds are numbers, but these bounds could also be functions. It could get more complicated. But for now, let's just think that these bounds are going to be numbers. So what's happening? How do these parameterizations work? And my apologies for the tilted axes. I must have been sitting at a funny angle when I drew this. So over here, we have parameter space. So I have a u-axis, a v-axis. And in the parameter space, u and v, the way I've written this, just map out a rectangle. So I'm allowing u to go from a to b, v to go from c to d, and they just take any values inside this rectangle. Now the vector function r takes these parameter values and maps to a surface in 3D space. So in other words, I pick a uv value, I plug it into r, I get a point on this surface. And so as I move around this square in parameter space, I'm mapping out this surface in 3D space. And so that's the idea behind these parameterizations. So we saw, we've dealt with a lot, functions of two variables where z equals a function of x and y, and then your x and y values are just in the xy plane. So that can be thought of as your parameters are x and y, and for every x and y value you get a z value, which is on this surface. But now we're allowing for more possibilities. X and y don't have to be your parameters. You can have parameters taking other values that aren't directly below the surface. And so that's what this parameterization gives you. It also allows you to have functions that give you surfaces that would not pass the vertical line test, right? If I have a parameterization over here, now I can have surfaces that wouldn't pass the vertical line test otherwise, but they're still functions because for every value over here, I still get a single value here. And we'll see examples of that pretty soon. So just as we had parametric equations for lines, parametric equations for curves, you can write parametric equations for surfaces. Just instead of writing the vector equation, you have three equations. They're the exact same equations that are in the parameterization, but you can split them up if you want. And then those would give you the coordinates of the point instead of a vector pointing to the point. It's just another perspective of looking at these things. Okay, let's look at an example. Sketch the surface represented by this parameterization, where the first component is 3 cosine u, the second component is v, and the third component is 3 sine u. We're told that u goes from 0 to 2 pi, and v goes from 0 to 4. So let's look at what's happening here. In the x and z components, the first and third components, these functions are making circles of radius 3, right? Because I have cosine, sine, and a 3 in front. So these are circles of radius 3 in the x and z directions. So you can think if we looked just in the xz plane, I would see a circle of radius 3. Y is a separate parameter, and y is just going from 0 to 4. Basically, what we have here are cylindrical coordinates, except now my polar coordinates are in x and z, and where I would have z equals z for cylindrical coordinates, now I just have y equals y. The only difference here is that my r is fixed at 3 instead of r being variable as well. So you can have cylindrical coordinates by just moving around the definition by having polar coordinates and two other components instead of x and y. And we'll actually talk about that later. So what do I get if I try to sketch this surface? I get a cylinder. A cylinder parallel to the y-axis because I just have circles in the xz plane and I'm moving in a y direction because that's a separate parameter. So I just get circles moving out in the y direction. That gives me a cylinder of radius 3, parallel to the y-axis. Okay, so that's one example. Let's look at some examples of coming up with parameterizations. So find a parameterization for an infinite plane that passes through a point with position vector r0 and contains two non-parallel vectors a and b. Just to remind you, a position vector is a vector whose components are equal to the point in space that it is pointing to. So the components of the position vector are equal to the coordinates of the point. So it's just a vector starting from the origin pointing to a point. Before we get to let me reveal the drawing and the parameterization itself, but let's focus on the drawing first to get an idea how it works. So we have some plane that passes through a point. This is the point it passes through. And so what we do is we draw a position vector to that point and say, okay, now I can get from the origin to this point, so I can get to one point in the plane. How can I get to more points in the plane? Well, I also have these two vectors in the plane. So I can go along these directions to travel along the plane. So first I go to this point, and then let's say I want to move in the a direction. And if I take multiples of this a vector, I can go anywhere along this line by first traveling to the point and then traveling along this line multiples of a. And then I could do the same thing traveling along this line in b. So I travel to the point and then I add multiples of b and I travel along this line. And if I take combinations of multiples of a and multiples of b, I can get to any point in the plane. So let's say I start at this point, I move this far in the a direction, this far in the b direction, I can get there. I can go this far in the a direction, this far in the b direction. I can go backwards in the a direction, backwards in the b direction. And if I take all possibilities, I map out the entire plane. So the parameterization, we use this vector addition idea of just adding multiples of a and b to travel through the plane. First, we move to the point that's fixed in the plane that we know. I add a multiple of a, I add a multiple of b. These u and v are my parameters, and we allow u and v to take any values in R2. Next, I'm not sure how useful this is. I just wrote out the components of these vectors. So r0 is just going to be the coordinates of the point that we know, the fixed point. And then I just gave similar values to a and b and wrote out what the parameterization would be just by adding all of these things together. But the idea is that we start at a fixed point in the plane. If we know two vectors in the plane, we can add multiples of the two vectors to move to any point in the plane. So we can reach any possible point. Okay, let's look at some more examples. How can I parameterize the sphere? X squared plus y squared plus z squared equals a squared, so a is fixed, and a is the radius of my sphere. Well, if I have a sphere, let's use spherical coordinates. In this case, rho equals a is fixed, so rho is not going to be a variable. If I write out my spherical coordinates, and instead of using phi and theta, I use these parameters u and v. So the first component is a sine u cosine v. The second component is a sine u sine v. And the third component is a cosine u. So here u is acting as my phi variable. So u goes from 0 to pi. V is acting as my theta variable. So that goes from 0 to 2 pi. Rho is fixed. So rho is no longer variable. Rho is a fixed constant a. That's the radius of my sphere. So the whole idea here, if you haven't noticed yet, is that we're taking a surface in three variables, x, y, and z, and we're reducing it to a function of two variables, just u and v. So we want to reduce the equations by one variable so that we can represent the surface with just two variables instead of all three. If we switch to spherical coordinates still have three variables, rho, phi, and theta, but because we're on a sphere, rho is fixed, so I'm allowed to eliminate that variable by replacing it with a constant. And that's how I get down to two variables. Okay, let's look at another one. Let's parameterize the cylinder, x squared plus y squared equals 16, where z goes from 0 to 5. So now we have a cylinder parallel to the z-axis, and it's just radius 16, so you can think of circles of radius 4, just stacked along the z-axis. So since we have a cylinder, let's use cylindrical coordinates. If I use cylindrical coordinates, I'm going to have an r, a theta, and a z. So z is going to be one of my parameters, and I already have bounds for it. Sorry. And then r equals 4 is fixed because in the xy plane, I'm making circles of radius 4, or in the xy kind of slices of this surface. The radius is fixed at 4. So then I can just write out my cylindrical coordinates. It would be r cosine theta, r sine theta, z. But now r is fixed at 4, so I've eliminated that variable. It's now a fixed constant. I'm using u for my theta variable and v for my z variable. So 4 cosine u, 4 sine u, v. I allow u to go from 0 to 2 pi and v to go from 0 to 5, because that's what I was given. And that gives me a parameterization for the cylinder. At this point, let me just say, if you don't want to use u and v, if let's say you're doing this by hand and your u's and v's tend to look the same, you don't have to use u and v. You can use any two parameters you want. It's just, I don't know how it became standard notation. It's just standard notation to use u and v as the two parameters. Okay, let's look at another example. Parameterize the cone z equals the square root of x squared plus y squared. Okay, so we've looked at this cone a couple times before in previous videos and previous sections. Now let's see if we can parameterize it. So I have z equals a function of two variables. Well, it's already a function of two variables. So I can actually just use x as one parameter, y as another parameter, and I've done it. But we're actually going to look at 3 different ways to parameterize this cone. And the first is exactly what I just said. We can use Cartesian coordinates. Let your first parameter be x, your second parameter be y, and then what does our parameterization look like? Well, the first component is just one parameter, because I let u equal x. The second component is just your other parameter, because v equals y, and then the third component, the z component, is exactly the function, because we have z equal to this function. And that gives us our cone. We let u and v be any number in R2, because this function takes values, x and y can be any point in the plane, in the xy plane. And that's done. We're done with that parameterization. The second way we're going to do this is by using cylindrical coordinates. And we've seen before that this cone, this particular cone, in cylindrical coordinates gives us the equation z equals r. If you're not sure, replace x squared plus y squared with r squared. Take a square root, we get r. And for this cone, z is only taking on either 0 or positive values, which is what we're also going to allow for r. It's either 0 or positive, so it's non-negative. Now, since z equals r, I can just pick one of my variables to equal r. That's also going to equal z, and this is how I'm eliminating one of my variables for cylindrical coordinates. And then my other parameter, I'm going to let be theta, and then I write out my cylindrical coordinates. So the first component would be r cosine theta, so it's u cosine v. The second component would be r sine theta, so it's u sine v. And then the third component would just be z. But now, since z is the same as r, I put u here. So u takes the place of my radius and my z component. So what's happening is, as u increases, I'm going up the z-axis, and the radius of my circles is getting larger. And that's how you get a cone. Here I take u greater than or equal to 0, and v goes from 0 to 2 pi, and this will give me the exact same surface that this parameterization gave me. Okay, and the third way we're going to parameterize this cone is by using spherical coordinates. So we've seen the equation for this cone in spherical coordinates before, v equals pi over 4. We've actually seen it twice before in previous videos, and you can derive it using that arc cosine formula. In spherical coordinates, my 3 variables are rho, phi, and theta. But now I'm fixing phi equals pi over 4, because that's the equation of the cone. So one of my parameters is going to be rho, the other parameter is going to be theta. And then I write out spherical coordinates. This is just writing everything out. I have u sine of pi over 4, because phi is fixed at pi over 4, cosine v, u sine pi over 4, sine v, and u cosine pi over 4. But I can actually take those values. They're all root 2 over 2. So I get a parameterization of u root 2 over 2 cosine v, u root 2 over 2 sine v, and u root 2 over 2. And that's a parameterization. Here u is non-negative, and v goes from 0 to 2 pi. What you might notice now is that the parameterization we just found is just a scaled version of what we found in cylindrical coordinates, right? Because all of the components are the same, except here they're multiplied by root 2 over 2. So we could factor this root 2 over 2 out, and we'd have root 2 over 2 times this parameterization. So they're mapping out the same surface. This is just mapping it out in a different speed. Speed kind of in quotation marks. Okay, so we can parameterize that cone 3 different ways. You probably wouldn't want to do it in spherical coordinates because you're just getting the same thing with a root 2 over 2 in there. But either of these would be good parameterization. So there's, just as there were infinitely many ways to parameterize a curve, there are also infinitely many ways to parameterize a surface. And depending on the context, maybe you would want to use this one, or maybe you would want to use this one. There might be a situation where you'd want to use this as well, but probably this would be better. Okay, let's talk about how to parameterize surfaces of revolution. If you remember surfaces of revolution from Calc 2, where you had to do all those crazy integrals, now we're going to parameterize these things. So just to remind you what a surface of revolution is, you take a curve and you revolve it about a certain axis. So here, let's just say we have a curve y equals f of x. I want to revolve that about the x-axis, and I have values for x. Then we can parameterize it. Since I have values for x, I'm going to let x be one of my parameters. And if I'm revolving about the x-axis, that means I want to make circles in the y and z direction. So I have cosine and sine for y and z, and the radius of these circles is given by the function. And that's how I get a surface of revolution. So u is one of my parameters. In y and z, I have cosine v, sine v, and then f of u, the function itself, tells me the radius of these circles. So let's look at a quick example. Parameterize the surface formed by revolving y equals 1 over x about the x-axis. X goes from 1 to 10. So what would this look like? And I've drawn this curve incorrectly. This curve in blue, I'm representing the original curve y equals 1 over x, but this should be in the xy plane over here. I just thought it would be easier to see here. So I'm drawing it actually in the xz plane, but you can use your imagination. So this is the curve I'm starting with, and if I want to revolve it about the x-axis, I just draw circles around the x-axis, and I get this surface. Now to parameterize this, x is going from 1 to 10, so I'm going to let that be my first parameter u. And then these circles, making circles in the z and y direction, so I have cosine v, sine v, where v is acting as theta, and then the radius of each circle is given by how far out we're going to get to this function, so the radius is just 1 over u, because the function is 1 over x. Okay, so there's a bunch of examples of parameterizing surfaces. In the next video, we'll talk about tangent planes to these surfaces, and we'll start finding the surface area of these surfaces.